Welcome back everyone and welcome to the final topic of Unit 1 Chemistry. Before we begin, I would like to just give you a very quick recap of what we've learned at since the start of the year and how this topic is going to fit into the big picture of chemistry. Fun fact, this topic is actually not listed in this map. This is the map of chemistry that was made by Dominic Willeman. It's a very good map that gives you an overview of the different aspects of chemistry, but for some reason doesn't actually have the topic that we're going to learn, so I can't even point it out. I'll just write it on the side. So we started the year now here with the idea of an atom, so we've done atoms, and we looked at the periodic table as well, so we've done that. And from atoms and periodic table, which are two concepts that you have seen in your junior years, we really focus on the different types of bondings, or in other words, we looked at how atoms can be connected to each other. And we have covalent bonding, ionic bonding here. We also looked at hydrogen bonding and van der Waals bonding, which is just dispersion force, just another name. And once we have an understanding of covalent bonding and intermolecular forces, we could really use it to start our first application of chemistry, which is in the field of organic chemistry. And we looked at plastic mainly. And I do have to point out that what you've learned in terms of organic chemistry in the past 4.5 weeks is probably it's just an introduction. This is a really deep and complicated field, and we need to spend a lot more time than 5 weeks or 4.5 weeks on it. Organic chemistry will come back. It is essentially the focus of Unit 4, so you're going to see it again next year. And also next year, when we get to Unit 4, we're going to extend organic chemistry to the field of biochemistry, which is the chemistry of the macromolecules. So we don't look at DNA, but we look at proteins, carbohydrates, and lipids. So this is year 12, organic chem and biochem. What we're going to do for the remainder of year 11 is actually start looking at the chemical reactions. So this is going to be the focus of Unit 2. And we're going to look at redox reactions, acid-base reactions, some of these types of reactions we're going to look at, and then we're going to see how these rules of chemistry will apply to probably my favorite aspect of chemistry. I like everything in chemistry, but I think this is my favorite, which is analytical chemistry, or the use of chemistry to analyze chemicals. I know, this is such a good definition. There are essentially two types of analytical techniques. The qualitative techniques allows you to determine the identity of a substance. So if you find an unknown substance, you want to know, is it ethanol or is it carbon? Does it have carbon in it? What is it? That's qualitative analysis. And we looked at qualitative analysis. We will look at them, those techniques in year 12. The other type of analytical techniques is called quantitative analysis. So quantitative analysis means that you want to know how much of something is in the sample. And this is a very, very important application of chemistry. If you think about it, we always want to know how much of something is in anything from food to medicine to, I can't think of anything besides food or medicine. But anyway, so you really want to know, or water, you want to know whether there's any toxin chemicals that is exceeding the recommended concentration or things like that. So that is a very big focus of Unit 2. But in order to get to this point, to understand analytical techniques, you need to understand how quantitative chemistry works. And essentially, there are two main concepts that unfortunately are not represented in this map that you need to understand. And that's the concept of relative mass. To be fair, we probably wouldn't talk about relative mass for too much. And the concept of moles. So two main concepts, and these two concepts are what we're going to spend the next week and a half to look at. Today we're going to look at relative mass, and next lesson is going to be on moles. Understanding these two will allow you to really understand Unit 2. So these are really, really important topics. Okay, that's my big introduction. This is the agenda for today's lesson. We're going to look at relative isotopic mass, relative atomic mass, relative molecular mass, and then I actually will introduce one technique. The first analytical technique that you're going to see is going to be introduced today, and that's the technique of mass spectrometry, which is Probably my favorite analytical technique as well. I'll tell you why in a bit. All right, let's start with a definition of relative atomic mass. By the way, we're going to use the word mass and weight like interchangeably in chemistry. I quite frankly do not care about gravity at this point. So I'm just going to stick to mass, I think. Anyway, relative atomic mass, you actually have seen relative atomic mass if you look at the periodic table that I gave you at the start of the year. The number that is listed in every box for every element, that is the relative atomic mass of that element. This is a definition of relative atomic mass taken from the textbook. Relative atomic mass is the weighted average of the relative isotopic masses of an element on the relative scale where carbon-12 is 12 units exactly. Very easy to understand. No problem? Any question? Okay, no question. Let's move on. This is a characteristic of an element. As I just mentioned earlier, if you look at the periodic table, every element has a relative atomic mass listed for it. And there is a symbol, which we almost never use, but the symbol is AR for relative atomic mass. And then later on, you have IR, which is relative isotopic masses. Okay, let's go back to the definition, because if you understood everything, good job, but I'm going to assume that you don't, so I actually have to explain things further. There are three things that you need to understand when you look at this definition. Weighted average, relative isotopic masses, and relative scale, where carbon-12 is 12 units exactly. So we're going to start, I think, with this one, which is relative isotopic masses. Before we start, let's talk about what isotopes are. I think this was a concept that you should have learned at the start of the year, but it's worth recapping. So isotopes are atoms of the same element, so they have the same number of protons or same mass number, sorry, same atomic number, but with different number of neutrons. So same number of protons, different number of neutrons. An element may have one or many isotopes. So this is the first example of the three isotopes of hydrogen. Ooh, isotope of hydrogen. So you have hydrogen 1, which only has a proton. You can see that all three isotopes have the same number of protons. They are all hydrogen, so they should all have one proton because the atomic number of hydrogen is 1. But deuterium has an extra neutron, so the mass number is 2. So mass number is up here. And tritium, which I almost never see, has a mass number of 3, so it has 2 extra neutrons. This one's really unstable. But deuterium is a very useful isotope of hydrogen. Another one that I think you might have seen is, so we look at carbon, there's carbon-12, which has 6 protons, 6 neutrons. Carbon-13 is an isotope of carbon-12, and it has 7 neutrons. And then you have carbon-14, which this is not stable. And I think anyone who learns carbon dating would have seen carbon-14 being an unstable isotope of carbon, and then eventually it will decay into carbon-12, and that's how you can date the well, you can date a substance. We don't talk about carbon dating in chemistry, but fascinating stuff. Anyway, another concept I want to recap before we actually learn anything new is the concept of mass number, because I think this is so far the only thing that you've seen that has the word mass in it, so it's worth telling you what it is and what it is not. So mass number is the sum of the number of protons and the number of neutrons in an atom. And because it is the sum of the number of protons and neutrons, it is always a whole number. You cannot really have 12.5 being the mass number. We use mass numbers a lot to distinguish between different isotopes of an element. So for example, I can have hydrogen 1 or hydrogen 2 or hydrogen 3. And that is how I would say these symbols as well, hydrogen 1, hydrogen 2, hydrogen 3. And that is to distinguish between the 3 different isotopes of hydrogen. Or I can have carbon-12, which just means that the mass number is 12, and there is carbon-13 or carbon-14. So we normally use mass numbers as a way to distinguish between different isotopes of an element. But mass number is not relative atomic mass. And I think you can tell because if you look at the periodic table, the relative atomic mass, a lot of the times, if not all of the times, have a decimal next to it. So you can't really have the mass number that is not a whole number. So these are not the same thing. And mass number is not relative isotopic mass either. Mass number is actually not a very useful number. It tells you how many protons and neutrons an atom has, and you can use it to distinguish between isotopes. That's pretty much it. It doesn't give you any concrete information about on the actual mass of an isotope or the actual mass of an atom. So don't get confused between these two. I will tell you what these two are, but they're definitely not mass number, is what I'm trying to say. All right, that's enough recap. Let's actually start the topic. So if you think about the words, so we had relative atomic mass and relative isotopic mass. So there's a word relative in it. So we're going to talk about what a relative scale is and what does it mean basically. I think some people probably already know, but anyway. Uh, well, actually, I hope most of you already know, but never assume too much of students. So a relative scale, this is just one way to describe a relative scale. It's basically a scale that is derived from making comparisons rather than making measurements. So when you say somebody is, I don't know, 1.7 meter tall, that is an actual scale. On absolute scale, that's not a relative scale. Relative scale is when you say somebody is taller than someone else. That's when you're making comparisons between two people. Normally, when you have a relative scale, one thing is going to be the standard, and then everything else is measured or compared against it. So I have an example of a relative scale here, and you see this a lot in restaurants or whatnot. This is absolutely not this is not an absolute scale. This is just a relative scale. So mild is medium is more spicy than mild, and then hot is even more spicy, and then there's hell, and then there's Mexican. Um, I mean, they do have numbers here, but these are not, measured against an absolute standard. And you can probably argue like something that's considered mild for one person may be hell for another person as well. So this is a relative scale that is not very clear in terms of what the standard is. Um, this is an absolute scale. The Scottville heat unit, this is going to be absolute. This is actually measured using a technique that we are going to learn in Unit 2. So I might explain how you can come up with this spiciness scale later in the year. But that's the difference between a relative scale and an absolute scale. Is that a relative scale is just things like mild, medium, hot, and then absolute, you have some actual numbers that is measured based on something else. We'll talk about this later. Anyway, so that's the difference. In the case of relative isotopic mass, the reason why we use a relative scale is because, first of all, an atom is too small, and the mass of an atom is not very practical. Like it's like something times 10 to the negative 23 grams. So it's just a really small number. And under no situation, okay, I'll say that again. Under the In the majority of cases, you do not work with one single atom. Like the majority of applications of chemistry in real life requires you to use more than one atom. So the mass of an atom is not very useful. It is, however, more useful if you can compare the masses between different atoms. So I don't care what the mass of carbon is, but I want to know whether carbon is lighter or heavier than, say, steel. Let's say, for example, if you want to replace a material that is used to make airplanes with another material. So people want to replace steel for titanium or graphite, which is carbon. And one of the advantages that people have suggested is that the replacement material is a lot lighter, so it doesn't take as much fuel to lift the plane up. So if you want to be able to make those replacements of materials, you need to know whether carbon is actually lighter than iron. Another example, because the year 12 students just did a stack on this, is on the concept of lithium battery. The reason why lithium is often used in a lot of portable devices is because it is probably the lightest metal that is also incredibly reactive. So you want to know whether something is heavier than something else. That's probably more important than what is the mass of an atom, because that number doesn't tell you anything. Anyway, that's a lot of talk for one simple point. So the relative isotopic mass, first of all, is the mass of an isotope. It's the mass of an atom of an isotope compared to the mass of an atom of carbon-12. So this is a relative scale. Your standard is carbon-12, so one atom of carbon-12 isotope. and you assume that one atom of carbon-12 has a mass of 12, and then you compare everything else against it. And the symbol for relative isotopic mass is IR. So let's say, for example, I'm going to assume that the relative isotopic mass of carbon-12 is 12.000, so 12 units exactly. If I say that one atom of hydrogen-1 has a relative isotopic mass of 1.008, this is essentially just saying that this hydrogen atom is about a 12th of the carbon atom. If you want to be very exact, it's a 12 and a little bit. So around 12 of the hydrogen atoms equals to 1 of the carbon atom. So this is just a reflection of how light this hydrogen atom is compared to the carbon-12 atom. You can also measure the carbon-12 against carbon-13. So carbon-13 is 13.003, and this is again just a reflection of the fact that it's a little bit heavier than the carbon-12. And you can have something even bigger, like this is an atom of oxygen-16, and it has a relative isotopic mass of 15.995. So it is a little bit heavier than carbon-12. So carbon-12 is just standard, and every other relative isotopic mass is being measured against carbon-12. Okay. The other thing I want to point out is because these relative isotopic masses, they reflecting a ratio between the mass of that atom and the mass of carbon-12 atom. So they don't have a unit because it is a ratio, really. All right, one more concept before we can get to the weighted average, and that is the concept of percentage abundances of isotopes. So this is an example. So we'll talk about chlorine here. Chlorine has two isotopes. These are what's the word, mass numbers. So you have chlorine 35 Cl, and you have chlorine 37. So two types of isotopes. So this pie chart, I forgot the name of the chart, actually represents two things. So the first thing, it tells you the actual relative isotopic mass of the chlorine. So chlorine 35, the relative isotopic mass is 34.97. So 35 is the mass number. The relative isotopic mass is 34.97 compared to carbon-12. And chlorine 37, even though the mass number is 37, the relative isotopic mass is 36.97. The other thing that you can see from this diagram is you're given the percentage abundance of each isotope. So 75.76% of all chlorine atoms are chlorine 35, and 24.24% will be chlorine 37. So if you pick up, say, 40, I think this is 40 chlorine atoms. If you pick up 40 chlorine atoms, about a quarter of them will be chlorine 37, and 3/4 will be chlorine 35. So this is what is called the percentage abundance of isotopes, because when an element has more than one isotope, it actually, I mean, we don't know why, but the percentage abundances would vary. It doesn't have to be a 50-50 split. In this case, 3/4 is this isotope and a quarter is the other, but you can have other distributions as well. So that's what percentage abundances mean. So if you have 40 of these, so you will have 30 atoms being carbon 35, and then you have 10 atoms being carbon 37. Okay, so that's percentage abundance. I mean, you can write it as a ratio. I think the only thing I want to point out is that if you have percentage abundances, they have to add up to 100%, because otherwise what happens to the remaining percent? And they can't add up to 200% either. That makes no sense. Okay,